Lenovo can help you implement artificial intelligence solutions to enable your organization's intelligent transformation. Investing $1 billion in cutting-edge AI technologies, Lenovo offers the world's most diverse portfolio of AI-ready products from the edge to the data center. Visit lenovo.com/AI to learn more.
And keep improving this whole project lifecycle of how could we get better and better and better. And in that process, how do we know we have gotten better is you apply these software to applications. I would like to see a ton of research software engineers out there solving problems.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey everybody, and Shaheen, great to be with you today.
Great to be here as usual, Doug.
We have a really special guest with us, leading light in supercomputing software, Sunita Chandrasekaran. She is Associate Professor in the Department of Computer and Information Sciences at the University of Delaware. She's also computational scientist at Brookhaven National Lab, and very relevant to our topic here, principal investigator for the Exascale computing project's SOLVE project. And SOLVE is one of those government acronyms. It stands for Scaling OpenMP with LLVM for Exascale Performance and Portability. Did I get that correct, Sunita?
That's absolutely right.
Okay, thank you. So welcome. Lots we want to get to with you. We certainly know and have read a lot about your leadership role in porting and optimizing software applications for the Frontier Exascale system. Maybe we'll just start with a pretty general question. Talk with us a little bit about some of the big challenges on the software side and working in the Exascale realm. How is that different from software, say, from mainstream HPC or traditional enterprise software?
Thank you. Thank you, Doug and Shaheen, for having me here. It's a pleasure. And yeah, let's talk about that a little bit. So I found the biggest challenges to be working in the Exascale realm is the hardware and the software of Frontier is new to all the users of Solve, which includes software developers, which includes application liaison, which means we have personnel in the project that work with ECP, Exascale Computing Project applications. And we have students, we have postdocs, we have research staff, and so on. The hardware has been evolving over the past 3-4 years, in the sense, as a team, we have used pre-Exascale system, pre-Exascale system, all the previous babies of Frontier, and kind of kept up with what is eventually going into Frontier system. So we had to play a lot of catch up with evolving software, AMD HP Cray software, and the hardware, which is totally new because up until this point, most of the traditional mainstream HPC systems had NVIDIA GPUs in their large-scale supercomputers. So this has been a challenge, yet an opportunity on how do you tackle the hardware that we haven't dealt with? How do you performance profile your application? What are the tools? What is the software stack? How do you integrate the current software stack to your existing software stack, which means what are the backends you would build? And then, of course, we'll introduce a ton of bugs. So how do you resolve them and so on? So those have been some of the biggest questions we have been asking along the way.
Great to have you, Sunita. Doug, you and I have talked about software forever, and a couple of episodes ago, we said we are going to cover it, and I'm so delighted that we're finally doing it and doing it with Sunita, who's been really in the eye of the storm as it relates to Exascale software in a big way. So as you mentioned, the hardware is new, the software is new, the HPC community has performance at its middle name, so everything is focused on high performance, but then the nature of software is shifting, the scale of it is incredible. So there's a massive complexity here, and it'd be great to see how do you go about solving it, and what did the software group for Frontier did that is now helping push the HPC community forward.
Yeah, thank you for asking. So with respect to the LLVM software as part of the Solve project, we have been looking into all the compiler implementations, runtime implementations, all the backend implementations that is needed for AMD type of hardware. And at the same time, the implementations that are being built are for the OpenMP specification, OpenMP features. OpenMP is a parallel programming model, a directive-based parallel programming model, which has been existing for a lot of years now, very widely popular. And they ratify features on a particular cadence based on what are the application needs and what are the community needs, etc. So those features continued to be ratified, and then came the Exascale project. Now we are tasked with creating implementations for those OpenMP features, and not only creating implementations, but also creating optimized implementations, which will be an iterative process. But at the same time, target frontier hardware, as well as, of course, other hardware that we could get access to, and keep improving this whole project lifecycle of how could we get better and better and better. And in that process, how do we know we have gotten better is you apply these software to applications, right? And these applications are also new, running on Frontier. They have never seen AMD hardware. They have never worked with AMD software. So where do we start? So yeah, we kicked off some of those preliminary ideas and preliminary projects on using the pre-Exascale systems, trying to create proxy apps or those mini apps, which are smaller versions or smaller kernels of these big apps, port them to these pre-Exascale systems. Of course, it never compiles and runs the first instant, fails. So you get up and you keep moving and try to understand where the failures are. And in these processes where we had created some validation, verification, test suite as well, in order to stress test some of these implementations to ensure they are even correctly running on the system. Does this answer your question?
Yeah, it does. So one thing you mentioned is directive-based parallel programming models, and that is the method of choice for separating the logic of the computation from the instructions you want to provide to the system on what hardware it's going to be running on. And that has been a path. And then you also mentioned validation and verification, which traditionally has been under the big umbrella of debugging, profiling, and such. But first, maybe I should just ask, what is the difference between validation and verification? Aren't they both
Right.
kind of the same thing?
Yeah, kind of, sort of. So the few things the scope of this validation verification project is we write functional test cases, CC++ Fortran, to verify the implementations of compiler implementations of OpenMP offloading features. By that, I mean those features of OpenMP that we need to make a program run on GPUs. So those implementations, right? So we need to verify them. At the same time, when we write these test cases, we also need to make sure they conform to the OpenMP specification, right? So there is some sort of validation going on there, in the sense we could write a test that we think is right, but when we put this in our GitHub, and by the way, the entire Sol project is open source, there could be a vendor compiler who could, create a PR and say, no, your test doesn't make sense, which means, is the test wrong? Is the specification convoluted? Or is this test correct and the implementation is incorrect? Or where is the problem, right? So that's where the idea of verification validation comes in, because it's not enough if we write functional tests case, just that. We also need to make sure they conform with the specification, and we also need to validate this across multiple compiler offloading implementations, which means if it works on AMD software stack, does not mean that we are good to go. We need to also, verify HP Cray offloading implementation, NVIDIA HPC SDK on Perlmutter, for example, GCC, because why not? And then LLVM. And we were also running this test suite on Summit, so IBM OpenMP offloading compilers. And we are also beginning to test on any Intel GPU access we have. So Sunspot in Argonne National Lab. So yeah, there is a bunch of permutation combinations going on with this validation verification, in short V&V project, to determine where the bugs are. And to complete that story here, when we identify the bug, we kind of alert the vendor compilers. And if we realize that there is a problem with how we interpreted the specification, we go back to the specification developers of OpenMP and tell them, hey, definition of this particular feature is convoluted. We need to revisit this, right? And so they go back and fix the English the text, the narrative of this feature in the specification. So we have been able to do that as well in the iterative process of getting a test, up and going.
Absolutely right. You can't do tests without knowing the specs, right?
Yeah.
Could I ask, we could look at, from your perspective, looking at the Frontier system, I was just looking at some of the figures around Frontier, almost 9 million cores and 90 miles of networking cables. It just sounds like the work you're doing to port and optimize software just sounds like a monumentally complex task. Do you have a sense of almost the character of Frontier, what it's like trying to work with a system at that scale? But also maybe anecdotally, when you have successfully optimized, debugged a system, what is the performance like once the software has been tuned, tested, and really well suited for Frontier? What are the results like in the end?
Sure. So while we are talking about the Solve project, I also want to slightly pivot to another project on Frontier. This is Oak Ridge National Labs CAR, CAAR, which stands for Center for Accelerated Application Readiness, which goes very well with the question you asked. So Oak Ridge CAR project chose 8 projects in 2019 to basically rip Frontier apart and put it together before it is opened up to the public, right? So one of my projects called Peak on GPU, which is Plasma in Cell on GPU, was a project chosen among the 8 across the United States. Now, the goal of this project was exactly what you asked. The project Peak on GPU as a code, as a plasma physics code, runs on Summit already. The challenge we were asked to meet is get me 4x performance on Frontier, right? So that was a challenge. And that's where we started with this Peak on GPU project because, so we started this in 2019, and then we were looking at the different possibilities of how do you exactly bring the software that ran on Summit, which is an IBM NVIDIA box, to an AMD CPU and GPU box. How do you do it, right? So that's where we started. And in the process, we noticed how the software evolved. And this is a software called Alpaca, which is a C++ template-based programming model that uses several different backends. So we had to build backends for AMD hardware, which means we had to use a lot of ROCm, AMD's ROCm. And imagine creating a new backend to target Frontier, and imagine everything that can go wrong. So literally everything that could go wrong went wrong.
Of course.
Yeah, because ROCm evolves as we speak, and it has evolved since 2018, 2019, when this CAR project kicked off. And then with every version of ROCm, we see newer updates, or it would make or break the previous versions we have used. Then we go back to the AMD vendor and we work with them very closely, AMD, HPE, Cray, and actually kudos to them for working with so many of us with so much attention that we filed bugs. They had to look into those bugs, help us resolve, because without that, we are stuck. There's no way we could move forward. So there were all those issues. Fast forward, with the CAR project, there was a particular metric we used, figure of merit. That's a metric we used for the CAR project. And with the idea of, where we head to from this figure of merit on Summit, we used almost all of Frontier, barring maybe a couple of nodes or what have you, and met the target. Met the target of what was set as CAR challenge. The X number of performance, the 4X performance from Summit to Frontier. That's what told us the amount of performance that we could get, out of Frontier with the code that ran very nicely, very effectively on full Summit, and how it could get 4X performance on Frontier and more, given single precision, double precision if we wanted. So we got 8X better performance on Frontier for double precision, 4X for single precision. But the plethora of work that went on in probing an AMD GPU to the core possible with profilers, performance tools to tweak the performance, right? And then throw this across 9,000 nodes, deal with NPI problems, deal with network problems, deal with, failed node and whatnot. And to get that scaling curve, I think that was a huge celebratory moment for us when we got that 4X performance last fall on this plasma in cell GPU code for Frontier.
That's brilliant. Leads to so many questions. So I'll just start with one. One of them, it points to just the whole software engineering space as a whole
Yeah.
kind of changing, evolving thing. It leads to obviously AI because, it can help it can use it, etc. It points to the community of software experts and engineers and HPC folks. So let's just start somewhere. And maybe the place to start really is the discipline of software engineering for HPC and how you see that evolving. We've talked, both of us, and also in the pre-call, the notion of a research software engineer, RSE, which is a flag that needs to be waved and is waved by yourself and Vanessa and a few other folks that I have noticed in Twitterverse, and it needs to get better understood. Let's talk a little bit about that.
Oh, that's a lovely, lovely question. It is a question very close to my heart because I would like to see a ton of research software engineers out there solving problems. With this Picon GPU case as well as Solve's ECP project, Solve's applications that we deal with, I see a success team. How does a success team look like, right? There are a bunch of computer science developers. There are a bunch of domain scientists who know their domain, what science problem they are solving. And there are these overlapping group of people that we call RSE, research software engineers, who are not only traditional software engineers, but also have those extra expertise as part of their portfolio, and extra knowledge on the domain they're working on. And this proved to be key for this Picon GPU's success. The team composed of 22 of us, and majority of my team is actually in Germany, in a national lab in Germany. And there are some 8 to 9 physicists, and there is 2 RSCs, and there is 1 PhD student of mine, and I have an undergraduate student also who worked on this project. So we are all computer scientists. There is domain scientists, there is an RSC. The RSC's role here was to sit together with the physicist and with my team to understand what the algorithm was to apply parallelism to it, which is what I would tell them, right? But this person would figure out what the physics is. This is Rene Vedera, by the way, from HCDR Germany. He would sit together with the physicists in HCDR and try to understand what the algorithm is. Then we would discuss to figure out, okay, this is the hardware, this is the software, this is the parallelization of the algorithm that could, get as far as getting those performance for us, and then apply or get the code to evolve to exploit the hardware feature set of parallelism. Without this particular combination of traditional computer scientists, domain scientists, and RSCs, I think it would be a really, really a challenging problem to meet or to get the performance that we want. And the same to do with Solve project. There are a couple of applications that falls under Solve's umbrella. There is OpenMC, there is QMC Pack. Those developers, while they are computational scientists, computer physicists, if you like, they also have that computational scientist knowledge, without which it would be very hard to apply, traditional parallel algorithm to a physics problem that I have no clue what physics is, because that's not my forte. Just like for the physicists, computer scientists is not their forte. So nurturing this RSC group and enabling growth of RSCs, giving different titles, literally helping them grow at different levels in their career would be really key to see some of these real world problems running on these large scale machines.
Artificial intelligence has evolved with the explosion of large language models and generative AI technologies. Lenovo remains on the cutting edge of these and other new technologies by collaborating with over 40 partners validated to be a part of the Lenovo AI Innovators Program. With over 150 AI solutions across 180 countries, Lenovo can help expedite your organization's intelligent transformation. Plus, the Lenovo Responsible AI Committee was established to rigorously vet all solutions to ensure the AI is used responsibly. Visit lenovo.com/AI to learn more.
The big takeaway, I think, for everybody, if they're not already up with the program, is really the emergence of research software engineer as a career, as a function that needs to be cultivated and viewed that way. And I think that's a really big difference from the small HPC sites, or perhaps the way it was decades ago, where the PI was also the programmer, was also the sysadmin, was also the user.
Correct.
And it was a small group of PhD students who all kind of came together and did everything. But then over time, as it expands, specializations emerge. And this, I
Mhm.
think, is a very important specialization.
Yeah, and it should be taken up very seriously.
Along those lines, getting back to Solve, one thing that impressed me in reading about the project and the strategy behind it is the way you've tried to nurture a community and pull together different stakeholders, if you will, to interact with the end users and with the vendors so that everybody's perspectives, issues, challenges, needs are being discussed and understood. Talk a little bit about how you've nurtured that pursuit.
Yeah, thank you. Thank you for asking. So I strongly believe in communication, communication of all types. And I think that is where the idea of getting different stakeholders to talk to each other emerged. And I was doing the Pecan GPU project before taking on Solve. So I was able to apply all the issues we had dealt with in Pecan GPU on Solve. So with Solve, what we do is we have been sending out some survey, for example, to the application developers, trying to ask them what features do they actually need in OpenMP implemented, instead of just taking the OpenMP specification and implementing all of it. Because why would we do that, right? This way it is more targeted. This way we are in communication. We, in the sense, we software developers in Solve are in communication with the application developers. And we ask them, there are like 20 features. Which features do you need? Why do you need those features? And then I would take them to the LLVM software developer community and tell them that, look, this is how we need to do, because this is how the app developers will benefit. Now, this is just two stakeholders. Now comes the implementation of these features, comes the input or the support that we need from vendors, right? Because eventually we are targeting their hardware. And LLVM is also being actively used. The upstream LLVM is actively used in HPE Cray as well as AMD's OpenMP software stack. So it becomes even more key to be in continuous coordination with the vendors to file bugs, to see if they have picked up our bugs, to see if they have a solution to our LLVM bugs, because we need them to solve the bugs for us as well as for them, right? So again, communication. And there are several pieces in flux, and I can't say we have solved them all, but a few things that I often bring up to app developers, software developers, old CF, the facilities, as well as the vendors, together they are called the Center of Excellence, COE, that let's have this transparent interface where we all see where the issues are. The app developers know what to wait on. The software developers know what bugs have been solved or yet to solve, by whom, what's the ETA. So we are not endlessly waiting for those. And then once it is solved, how do you tell me that this bug is solved, right? How is that process even practically going to happen? So yeah, these are some of the communication challenges we have and some of the things that we are trying to address through talking to the different stakeholders and keeping everybody informed in a uniformed manner that these different pockets, there are these different problems, and these are the point of contact who are working on it. And this is the team you should go to speak to, so that you don't create a ticket and send the ticket to a whole different new team who would not know that there's another team solving the same thing. So that's one angle. The other angle we have also been working on is building this OpenMP community with user talks, where we bring users and or even developers to talk about how they have used OpenMP in their code, which is so important, because then somebody else on the call who is an application developer would learn what not to do, right? Because they have actually seen these errors or mistakes or issues, challenges faced by this app developer A. So the app developer B could learn from these facts and results on what are the flags to use, what are the compiler flags to use, what are the performance tools to use, profiler tools to use. So this way, there is a community being built. We have also done hackathons, 5-day hackathons, pre-COVID and post-COVID. We started off all these Zoom activities, multiple days, multiple weeks rather, and also using Slack as an effective way to keep in touch with all the teams, where Solve members will act as mentors, and we will bring in all applications that need LLVM OpenMP support to run their applications, and literally pick up Zoom rooms, right? Put apps developers in different rooms, and the mentors would float. across these different Zoom rooms to go check what the problems are. And we will bring in other mentors from vendors as well as facilities who have helped us a lot to make these hackathons very successful. And at the end of this hackathon, when you see the final presentations, you realize how much was solved in these, several days of hackathon. So yeah, it's all about community building at the end of the day, because we need everything to sustain for a longer time.
Yeah, I'm also seeing a growing presence on Mastodon, and there is a mastodon.hpc that has emerged that is quite good. So that's also recommended channel for participation. One thing we haven't talked about, and maybe we should, is of course AI. It's unavoidable and sometimes repeated too much. However, when we're talking about programming environments in general, it's an area that simultaneously needs all the disciplines that you mentioned and could even participate in all the places that you mentioned. At one end of the spectrum, you really need all of these disciplines and expertise to write the AI code that is being applied to various things. At the other end of the spectrum, you could use AI to do the programming for you eventually. As much as that is probably not an immediate thing, it's starting to show up. What is your perspective on that? And how are these big centers looking at that possibility?
Yeah, that's a very topical question, right? So some of the things we brainstorm internally is, for example, the validation verification test suite. Right now, we are manually reading the specification, the narrative, in the sense, a definition of a feature in the specification, which is of over 1,000 pages now, and translating those text to CC++ Fortran codes. What if we fed this to an AI model and automated the process of scraping through text, converting the grammar into real code, right? So that's a possibility, and we are thinking about that a little more seriously this year than last year, given the AI explosion and the tools availability. So that's one angle. At the same time, like you said, I don't think we are that far ahead with AI that we could just trust the kind of code it would emit, right? So there is still some manual intervention involved before we can tell that we are comfortable with the code that it generated. So, there's a lot of confusion in the community, and you read articles and tweets and stuff that AI would replace. And my strong opinion to that is AI would shift the job of a software programmer.
Exactly.
It couldn't replace,
I think it's called the law of conservation of difficulty.
Yeah, there you go. So it can probably speed up some parts of your code. And yeah, there are tools that do that. Again, does it speed up to the extent that you would have expected it to speed up? That's a question, unanswered question. But well, we have the tool that we could improve to do those jobs for you. But it still requires the human to think of algorithms, think of the real world code, think of a, prediction model. Now we have this poor air quality going on almost in the Northeast, for example. Do we have a weather model that would have predicted this sort of air quality deteriorating the entire week? And funnily enough, I noticed my smartphone weather app showing that there is 20 miles visibility, and it's pretty clear. That is wrong. So you see, that's what my weather app says, and I can't see my neighbor, technically speaking, and that's not 20 miles away. So yeah, AI could do so much, but it's shifting how humans are thinking to program. And coming back to solve, V&V, the validation verification is one way we are thinking to use or apply, AI models of how we could automate some mundane parts of programming and relieve the programmer from thinking those aspects, so the programmer gets time to think of some real problems.
A worthy goal, yes. For the Solve project, by the way, at what stage are you in the life cycle of the project, or does it actually have an end date, or will you just keep working on these applications until ECP itself is shuttered? What's the projection moving forward?
Yeah, it's a good question. So definitely we will be doing what we're doing until the end of ECP project, because we are in a phase where Frontier is available, right? We have started to use Frontier directly. Prior to that, we were using Crusher, which is pre-Frontier. So now we can log into Frontier and run all our codes, which means it only opens up, more tweaks that we need to do to our software. Although Solve focuses on node programming model, which was Crusher by itself. But yeah, scaling applications and stuff. Beyond ECP, there is certainly, concern is a strong word, but there is certainly lots of ideas on how we could sustain what we are doing, right? And trying different ways on how we can still keep the lights on, because LVM, VNV, OpenMP specification, these all were already ongoing before ECP happened. Now, after ECP happened, we only got pumped, and we got more money, and we got to hire more personnel to do the cool job, for the last several years, and we made a lot more progress, which we hadn't prior to ECP project. This was really, really great. Now, how do we sustain from here is something that we all have been discussing internally. After the end date of ECP project, how do we keep this going? Which means, do we go after newer solicitations, or do we tie in collaborations with existing packages? And there are those E4S packages, for example, ECP packages to which we could tie VNV, for example. So it keeps running, in the background, instead of us trying to run it independently off of those existing packages. So there are ideas, and we have started to discuss which directions to go, because we would love to keep doing this, but we have to get creative to keep doing this.
So, Sunita, tell us, if you would, a little bit about your background and how you arrived at this point, maybe a bit about your career path.
Yeah, you're taking me 15 years prior to where I am. Which is a good journey. So it's good to think about it. So quickly, my bachelor's is in electrical electronics, and if I think back as to, back then I wanted to do computer science, bachelor's of engineering in computer science. But I very much appreciate that I have an electrical electronics background in my bachelor's, because that's when I could play with hardware. And the more and more and more I get so intertwined with HPC, I am beginning to realize how much I love to work on new hardware. So that's where I started. And then fast forward, my PhD topic was actually embedded systems, which is little boards that you could connect to your laptop. Especially FPGAs, which is field programmable gate arrays, ASIC, application specific integrated architecture. FPGAs especially are tough nuts to crack, and there aren't cool software that would readily work on them. So spent a lot of time hacking my way through compilers and create translations and whatnot to get a C program running on FPGA. That was precisely my PhD topic. Little did I know that very soon after that, I'll be working on computers that are the size of a building. So that's what happened in my postdoc, which was in University of Houston. My PhD was in Nanyang Technological University in Singapore. Postdoc was with an HPC group under Dr. Barbara Chapman, which is where I started to really work closely into parallel algorithms, high performance computing, OpenMP, OpenACC, etc., etc. Fast forward 2015, I joined University of Delaware, which was great because I started to build my own group of PhD, master's, undergraduate students, heavily got invested into compiler runtime programming models. But very nicely, it also opened up opportunities to work with applications. So there is solar physics application from National Center for Atmospheric Research, NCAR, Colorado, Picon GPU. There's a biophysics code. There is nuclear physics code. So all that opened my eyes into how to create software that applications can actually use, rather than just creating software because I like to create software. That's where the RSC component, interdisciplinarity, and the communication of science to non-computer science background, that's where all those ideas stem from. So here I am. I got my tenure 2 years ago, so now I'm an associate professor in this university with a group of 22 students, plus all these cool projects to work with.
Brilliant. Sunita, congratulations on your wonderful career. Thanks for your time today. Really great conversation, and looking forward to the next opportunity.
Awesome. Thank you both very much for asking these insightful questions. These are really, really wonderful.
Okay, thanks so much.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.